Hello folks, welcome to Rational Science, the only site on the internet that does physics. Everybody else does math and magics, movement of concepts. What are we going to talk about today? Well, we're going to talk about special relativity, and within that, the special case of mass. They talk about the increase of mass, whatever that is. Can mass increase because an object travels close to the speed of light? We'll find out. Anyways, what is special relativity? Well, here we can see a little introduction. Here it is, okay? You've probably seen this somewhere, and here we show it to you one more time. Yeah, special relativity is like entering the twilight zone. Okay, that's what it is. So, if you looked at the twilight zone, you're looking at special relativity. Einstein didn't invent anything new. Or you could say that the twilight zone did not invent anything new. It was already there. Anyways, what is special relativity? Well, special relativity is specifically the world of flatland. In special relativity, in flatland, right, you cannot fall downwards because there's no gravity. Straight line, straight flame, okay? So you cannot fall. It's built, special relativity, on a world called flatland. It's all flat. Okay, there's no gravity, and it's funny that I have here Mr. Stephen Hawking, and he puts in his book that he was kind of smirking at a woman who said the world is really a flat plate supported on the back of a giant tortoise, standing on turtles all the way down. Apparently, this was a woman who said that to Bertrand Russell. And so good old Stephen Hawking, he kind of laughed at her, like saying, this is what people believe out there, flatland. But it turns out they believe in flatland as well, because here you have good old Stephen Hawking, and he says the following. He says, we are only one time dimension and three space dimensions in which space-time is fairly flat. Okay? That's what we see, right? And what's the issue? He continues, he says, why did one time dimension and three space dimensions flatten out? So yeah, he's talking about flatland. That's the world of special relativity. In fact, he's not the only one who says that. Here you have an article from Astronomy Magazine. It says, what shape is the universe? As far as cosmologists can tell, space is almost perfectly flat. So flat earthers, eat your hearts out, okay? But what does this mean? And he says, the article says, the most cosmological evidence points to the universe density as being just right and that it expands in every direction without curving positively or negatively. In other words, the universe is flat. So we're not talking about the flat earth anymore. Now we're talking about the flat universe. And of course, if the universe is completely flat, I guess the earth is flat as well. And here's Discover magazine says, does the universe go on forever? Is outer space finite or infinite? Explore this age-old question, he says, and then they answer, a few generations of telescopes, Kobe, WMAP, and Planck, sought to understand the shape of the universe. Was it curved like a ball or flat like a piece of paper? Now that's straightforward. Is it flat like a piece of paper or round like a ball, right? All three telescopes say the universe is flat. Okay, so I guess Stephen Hawking was laughing at himself and at his colleagues because they all believe in that the universe has the shape of a piece of paper, which is flat. What else can we say? And in fact, they illustrate this. This is the universe they illustrate. You either go with a finite universe or the infinite universe, and you can go with the infinite flat universe. And they say our universe is like that flat one there, okay? So I think there's no mistake. Special relativity specifically and general relativity in general say that the universe is flat. And in the case of special relativity, they're going to be playing around with this flat universe, and they're going to, work with time, with mass, and with length, okay? Actually, distance, as we covered in the past, distance traveled. And they're going to play some fancy things that, approach the twilight zone, actually exceed the twilight zone. The twilight zone got all the ideas from special relativity. Okay, so what happened? Well, last week we talked about the fact that these people are trying to, violate the rules of special relativity today. And why special relativity says that you can only travel in the best of cases, right? The speed of light. That's the limit, the speed limit of the universe. Nothing can travel faster than light. Nothing that has a body, right? And but they had to invent something to overrule that, to bypass that law of the universe. So they invented wormholes, they invented tachyons, they invented warp drives, they even invented the chronon, particle of time. So they have all these inventions, all these notions, all these ideas that they've come up with to try to beat the speed of light. They don't like the speed of light. It's a limitation, and you can understand why, because when you try to get to the nearest star, right, like Proxima Centauri, it's 4.3 light years away. That means traveling at the speed of light, assuming we could achieve that, right, or very close to it, it would take 4.3 years just to get one way, 9 years approximately, round trip. That's a long time to wait for a trip, for an expedition. Who would fund it? Who would pay for such a thing? So no, they had to beat the speed of light. They had to show that there was some magical way to go faster than light from here to the nearest star, let alone to other stars. They had to give hope, not only to the other mathematicians, but to the world, because people would start asking, well, hold it, takes 9 years to do a round trip to the nearest star. When are we ever going to do that? Hey, don't panic. We can go faster than light. That's the message, right? That gets across. And what is the problem with all that? Well, a lot of that is a problem with definitions. Okay, here's a definition of motion. That's the first one that they needed to tackle, and they never did, in all of mathematical physics. Not just special relativity, general relativity, quantum mechanics, string theory. In all of mathematical physics, there's not a single rational definition. In fact, there's not a single definition. In most cases, or I'd say all of them, they simply tell you, we don't know what time is. We don't know what a point is. We don't know what a line is. We don't know what mass is. They have like 7 different definitions. They don't know what energy is. So they have all these non-definitions. And yet they use all these words every day. And you say, how can they, express their ideas? How can they explain a theory if they don't have any definitions of the main words, the critical words they're going to use to make their case? I hope you're following me here, what I'm saying here. Yeah, if you don't have a definition of your words, how can you express your ideas? How can you express your theories? Does it mean that they don't understand it? Absolutely. If they don't understand it, can you understand it? Absolutely. Okay. So here you have, this is my take on this. Many living entities have the superpower known as memory, right? Almost all mammals, you would say, or lots of them at least, right, have memory. I don't know about insects. Maybe birds have memory, yeah. Humans, for instance, can record in their brains the previous location of objects. Okay, so you know that there's been a previous location, like, you take a lion, lion already understands that there's a previous location of the deer, and then what follows, they sense motion. But motion is out there. And what I say there, because of this, humans perceive motion and premiere the movie in their brains, because they have memory. See, if you did not have memory, you'd only see location here. Then you lose your memory. You wake up again, or you recover your memory, or whatever. Suddenly you see, or your sight really, and you see the new location. You turn off, you see the new location, and you don't have memory that this thing moved. And it's only thanks to memory that we, perceive this motion. However, objects do indeed change locations out there, outside of you, outside of your brain, right? Falling from a tree or shutting a door on your fingers, that proves to you that there is motion because you feel it in your own, body. Things move by definition if they occupy sequential locations, whether there is an observer or not. Some people say, tree falling in the forest, does it make sound? Well, sound is motion, right? And so the tree falling is also motion. Whether there's someone there to see it or hear it, we don't care. We have a definition for sound and for the tree falling. We don't need to have an observer. And so motion, two or more locations of an object. Okay. So we do have a definition for motion. It's two or more locations. If an object occupies two or more locations, we say it moved. That's physics. We're done. That's how simple the word motion is. And what was interesting is that Newton was not able to define the word motion, among others, right? Or time or space. He just says, because we all know what it is, or have an intuitive notion of what it is, right? Okay, if that's motion, what is time? Well, the difference with time is that whereas motion is out there, time is not out there. Okay, there's no ticking clock, nothing flowing out there. Relative or absolute, doesn't matter. There's no time out there. Time is in here, okay, in the brain. Whereas motion is out there, time is in here. Okay, there is no process called time occurring out there. No ticking clock, no pendulum, no nothing out there. The earth goes around the sun, we say it's a year. Year is a notion we created. The earth just goes around the sun. That's it. There's no God of time saying, oh, that's 1 year. No, we defined it that way. Okay. Time occurs in the mind of the observer. The two objects are moving out there. The two objects move out there, but time is happening in here. Okay. There's no time out there with the two objects moving. It's the comparison that you make. Time involves the motions of two objects, memory, right? You need that memory, and a comparison made by an observer. You need to compare the two motions. Here's an example. The earth going around the sun, okay? That's one motion. Another one is the second hand of your clock, right? And it goes around. When it goes one tick mark from one tick mark to the other, we call that 1 second. The earth went around the sun 30 kilometers. And if you add those 30 kilometers up, you have a full year. That's what time is. It's a comparison of two motions. Okay, I wave my hand and I look at my clock and I say, it took me what? So many seconds. 3 seconds, 2 seconds, whatever. Okay, so time is a comparison of two motions. That's what it is. And no one has ever defined time. In fact, it would destroy all of special relativity if they did define time. So they had better never try to define time, because it will destroy special relativity. Not to mention also general relativity, which bases a lot of its, ideas on special relativity. That's where it originated. General relativity originated with special relativity. Okay, so when did time start? Well, according to the mathematicians, this is when God set the world in motion. He turned on time at some point in time, right? They say it's like 14 billion years ago. Okay, and that's how our universe was created. Of course, religious folks say, "Hey, where did the singularity appear that started the whole process?" That's the issue. And of course, the relativists can't answer that question, especially on the one hand, they're atheists in general, and they don't believe that there was a God that set things in motion or created the singularity. That's one problem. And so people say, well, where did the singularity come from? How do you create something from nothing? And they don't have a definition for nothing. As always, they don't have definitions. And they never define nothing. And they think space is a thing. And so we have this thing called space and this thing called matter, all these things, and they came out of nowhere. And so some of the mathematicians take the view that, well, we don't answer questions of what happened on the first frame of the Universal movie. We just start at the second frame when the singularity is already there, and we have no way of knowing what happened before the singularity or how it came to be. And others have this oscillating universe where the universe, collapses and then starts again and collapses into a singularity and then begins again from a singularity. So it's like a cyclical one. So they have all these ideas of how the universe, came into being, how it started, how it progressed, and how particles, were created, right? And here you have the Universal movie that they set in motion, that the mathematicians set in motion. In other words, they never start at the singularity. Their universe always starts is always in the middle of the film. It's always moving. At no point does it remain static that you can identify the first object and say, this is where the universe started. And here it is. Watch it. Here's the movie. Okay. You see the singularity just getting bigger, I guess, becoming this thing we call the Big Bang. Okay. What we know as a Big Bang. Okay. And it's always in motion. You never see it stopping in a way that you can analyze, especially the first frame in the film. Okay, and that's the issue. So they don't have a starting point for the for the movie, for this great movie that they sell, which is the Big Bang Theory. Okay? How do we do it in science? We do it a little different. We start here. We start with the Universal movie, and we say that, assuming or you can picture this or visualize this as a movie, right? In a single frame of the Universal movie, every atom is at a given distance from every other atom in the universe. So if you had God's eyes and you could see every single atom in the universe, right? Right now, right? You take a snapshot of that, okay, of that image, right, of with your camera, with your super camera. Here it is. You're taking a snapshot of it, of the universe. We'll call that Father Universe, right? You take a snapshot of that, and you see every atom in the universe only at a given location and at a given distance from all others. And that is essentially the definition of location, the set of all distances from all objects to a single atom or to whatever you designate as a target. Could be you, right? So time is an invention of living entities. We invented time because we have memory. Father Universe only recognizes location, a static concept. All concepts up there that you see in the yellow square there are all static concepts. Object, distance, location, existence, all these are static concepts. There is no motion involved in the definition of any of those words. Okay? Father Universe is what? Every atom in existence at a given distance from all others. That's Father Universe. Okay? All atoms in existence can only occupy a single frame in the Universal movie. So there's only one frame at any point in time, you could say, or at any point in motion, at any location. Right? There's only, or single frame, right? There's only, every atom in the universe only occupies a single frame. Next frame, you do not have a cloning of every atom. In other words, when the atom, we say, moves, every atom in the universe moves to a new location and it no longer exists in the previous location. It's not like the atoms are cloning themselves, okay? That's an important point because that destroys all of special relativity. Special relativity has this memory where they say, oh, but the atom was over there, now it's over here, but it's still over there, and I can go back in time and stand on that atom. No such monster in the Universal movie. So what serves as a backdrop to all these atoms we collectively refer to as matter is known as space or vacuum. In other words, nothing. What is something? An object, that which has shape. In other words, that's a thing, an object, right? Something is that which has shape. What is nothing? Also known as space or vacuum. It's that which doesn't have shape. Okay, we have that which has shape inside of, or you could say encapsulated, or whatever serves as a backdrop is this thing we call nothing or space. Okay, that's the situation there. And Father Universe has no memory, so Father Universe doesn't keep track of time because time involves memory. You can't do time without memory, right? And so here we have good old Father Universe. He just woke up. He goes to sleep for an eternity, right? So Father Universe does not recognize a universal movie. Okay, that's us. We see the movie. We see the moon moving. We see the sun, the earth going around the sun. We see motion, right? Father Universe doesn't recognize a movie. Father Universe only recognizes location, a single frame in a universal movie. Motion is an alien concept to him. Father Universe is only aware of location. In the first frame, in the next frame, all of the atoms that comprise Father Universe are all at a different location. So Father Universe is not aware of this because Father Universe went to sleep for a gazillion years and just woke up from the last frame. Okay? So he awakens. All he knows is at that moment in time or moment of motion or location is the distance of every object, of every atom in the universe from all others. That's all he recognizes. He's not a spectator. He's merely an actor. And he doesn't analyze himself like we do him. Okay? So Father Universe, he goes to sleep in every frame. Okay? Goes to sleep. He doesn't know anything about anything. All he knows is he's got all the atoms there, right? All at a given location. Goes to sleep for a gazillion years, wakes up in the next frame, right? Again, he just sees every atom at a given location. Okay, so he doesn't know anything about motion because he doesn't remember what happened in the previous frame. He doesn't know what's going to happen in the next frame. All he knows is at this point in time, every atom has location. Then he goes to sleep, wakes up again, next frame. That's the way it works. Okay, Father Universe does not recognize motion or time. Okay, Father Universe also suffers from amnesia, because again, he doesn't recognize memory. And so Father Universe suffers from amnesia. Father Universe lost his memory. Father Universe doesn't remember anything. He does not have a filing cabinet or save files in his computer. Okay, so good old Father Universe, if you want to travel back in time, you better not consult him. He doesn't have any memory. He doesn't know what that is, right? So it's funny when you have people like Brian Greene here, it's shown him in the past, and he's going to jump into a wormhole and see himself in the morning a few hours earlier and shake hands with himself. Yeah, that might be in the religion of mathematical physics, in special relativity, right? But not in science. In science, this is ridiculous. It's irrational. It should not be even shown as science. And this was from a documentary on science, so you can see that what they're feeding the public. They're feeding garbage to the public. This is nonsense. Wormholes and going back in time, absolute nonsense. And why did they have to create the wormhole? Why did they invent the tachyon? Why did they invent the warp drive? Because they needed to go faster than light. Otherwise, we have no hope here on Earth. We have no place to go. We all die here on Earth. They said, no, we got to give hope to the mathematicians so they can continue doing equations, developing equations. We have to give hope to people who ask, mathematician, are we stuck here on Earth? No, we're not. So we're going to go to Mars, and we're going to the nearest star, and finally we'll conquer the whole galaxy and maybe the whole universe. That's the story they give you. And the question is, can we travel faster than light? Well, if you leave it up to special relativity, it says no. But laws are there to be broken, right? That's why they made these laws, these mathematical laws. Okay, so here's the universal movie. And one of the problems is that you cannot time travel. Okay, and so no matter how fast you travel, even if you were to travel faster than the speed of light, you would not be able to time travel, meaning you can't go to the past or to the future because they don't exist. That's how simple it is. And here's just a way of illustrating that. If you're in frame 631, you're just at a given location with respect to every object in the universe, no problem. Frame 632, do you make a clone of yourself in the next location, or did you move? Which happened? I mean, should there be two people there in that frame? Is that what Father Universe would find every atom in the universe and two of you? Suddenly, there's two of you, and maybe of every atom in the universe. Next frame, you get three, and so on. You're moving down the line, and there's always a new you. So is this what happens, that we create clones of you in every location, every frame of the film, in Father Universe's film, the one that he doesn't remember having? He only recognizes a single frame. And so, yeah, we have a problem. And then so when people say, well, this guy, the farthest guy on the right there, he wants to travel to frame 633 to shake hands with himself. Several hours earlier, number 3 there in frame 633, can he do that? Can he travel through a wormhole or through top of a tachyon or warp drive or whatever? Can he go back and shake hands with that guy? No, because that frame 633 does not exist any longer. That's the problem. Okay, so, you have to look at this from a rational point of view, and that is that we cannot time travel with or without a wormhole, assuming a wormhole existed, right? We're such monsters out there in space that you could just get into the tunnel with your spaceship or nude or whatever and go to the past. What are you going to encounter? Where's the past? What atoms are you going to encounter in the past? The atoms are no longer where your memory says they were. Okay, that's the issue. Up here, you can memorize anything you want. You can imagine going back and talking to Atahualpa or Moctezuma. You can do that in your mind. But do these atoms called Moctezuma, are they still there? Right? Are these atoms assembled there and you can go back and shake hands with him? I don't think so. And this is the issue. The issue is that these people are selling garbage. They're selling garbage when you talk about time travel to the past or to the future. Again, the future hasn't happened, so and the atoms are not there where your mind is. Your mind is in the future, but the atoms are not there. Your atoms are right here. That's the real world. And so are your atoms of your body going to travel to what? To the future of Earth, that the atoms are not there yet? So keep all that in mind. This is the difference between them. Here you have the way irrationality works, which is the top particle, right, or ball or whatever, object. And you can see that it just occupies different locations. But the mathematicians have this notion that they make clones of all these balls and that you can go back in time to whichever one of those balls. Okay, each one at a different location, but the location is still there because of time, which involves memory. So you can hop to the past and land on one of those balls. And that's what's irrational. Objects can now occupy only one location at a time. Oh, I went out of focus there. See if I can get myself back in. I don't know what happened here. Maybe I drank too much. There we go. I think I'm getting myself back. I think I'm back. Okay, so, they've been developing for the last 100 years equations on all this inexistent stuff. Everything related to special relativity is garbage. It's nonsense. None of it survives rationality. But then they've created, the warp drive, the tachyon, the wormhole. They created dark matter and black holes, which black hole is zero-dimensional. How can a black hole be there if it's zero-dimensional? It's not even an object. And you say, Bill, it's not zero-dimensional. Yes, it is. Okay, it is because Subramanian Chandrasekhar Indian guy, he won the Nobel Prize in 1983 for proving mathematically, right, that radius of a black hole is exactly 0. Radius is 0. That sounds like no volume, no size, no shape. Yeah, that's what it is. Singularity is absolutely 0. And obviously that's one take. They had to get around that, so they created the other version. And that is that singularity is really a point of infinity, and you never reach infinity. Meaning that all the matter, which supposedly was crushed out of existence, the sun that collapsed to become a black hole, a singularity, all that matter supposedly was crushed out of existence. There was no matter, meaning no mass, meaning a black hole has no size or no mass. And they said, no. All the matter is still there between the event horizon and the singularity. It's still falling. It's falling forever. It'll never reach the singularity. And that's the other version of a black hole. So they had to solve the problem, and some of them believe in one singularity. The other people believe in the others, so you take your pick. Okay, so what they've been doing is developing equations for all this nonsense, wormholes and space-time and virtual particles, right, that fill the vacuum, right? They have black holes, the tesseract, which is the 4-dimensional whatever, which is really a 3-dimensional version of 2 nested cubes, etc. They have all this nonsense. Okay, and so now they're, I guess, developing equations for leprechauns and unicorns. So that's the state of special relativity in a nutshell regarding time. We're going to get into now how that affects mass. It's important to give that as an introduction to know where we headed next with mass. But we're not finished with time, really, so I have to cover this base, and that's the issue of simultaneity. Okay, what does simultaneous mean? And boy, the special relativist, especially Einstein, he got tied up in knots trying to figure out simultaneity. And here it is. This is the definition from the Wikipedia. In mathematical physics, I put the mathematical in there, right, because that's not physics. The relativity of simultaneity is the concept that distant simultaneity, whether two spatially separated events occur at the same time, is not absolute. Okay, so they're saying two events do not necessarily happen at the same time, but depends on the observer's reference frame. Okay, that's when they happened. When each observer, according to his reference frame, says it happened. Okay? This became a central idea in the special theory of relativity. So keep in mind, special relativity is based on this nonsense that it depends on the reference frame of the observer. So there is no simultaneous occurrence. Like I say, if you shake hands with someone, that did not happen at the same time. For you, it happened this time. For him, it happened at another time because you were in a different frame of reference. Kind of. That's more or less like it is. People say, well, Bill, you're making a joke out of these people, but that's what it amounts to. Okay, it amounts to saying that, if a star exploded in a given frame of the Universal movie, and everybody sees it at different times, well, the star exploded in that given frame of reference, in that frame of the Universal movie. What people perceive, what they measure, what they think happened is different. Okay, and so again, special relativity has to do a lot with observers, and in science we kill the witness. There are no witnesses. There are no observers in science. We just need to explain what happened, and for that you need to establish the objects and the definitions. And that's where special relativity just falls apart completely. According to the special theory of relativity, it is impossible to say in an absolute sense that two distinct events occur at the same time if those events are separated in space. Absolute poppycock. Absolute poppycock. They say that there's no way of telling. It's impossible to say whether two events happen at the same time or in the same frame of the Universal movie, essentially. If one reference frame assigns precisely the same time to two events that are at different points in space, a reference frame that is moving relative to the first will generally assign different times to the two events. In other words, what they're saying is, if you're moving and I'm moving, we're both moving with respect to, a supernova, and you're in one planet, I'm in another, we're going to see different things, so I'm going to assign a different time according to my clock and my calendar than you and yours. Well, I don't care about that. That's measurement. The question is, did the supernova happen in a given frame of the universal movie? That's the question. And these people are trying to tell you that the event did not happen in a single frame. That in your frame, it happened in your frame of reference, according to your location, your distance from the event. This event happened in this frame of the universal movie. And in the other fellow's version, it happened in a different frame of the universal movie. That is absolute poppycock nonsense of Einstein and special relativity. That has no place in science. Okay. And again, they talk about a car crash happening in two places, and the question is whether, the guy sees it, in London, whether he sees it from a spaceship or whatever. Absolute nonsense. Let's show this in images so that people are convinced of the argument, so they can use it against any special relativists out there. Okay, let's make sure we smirk and laugh at them and make if you can't beat them, ridicule them. That's my take on that, okay? So here it is. Here's two supernovas happening in a given frame of the universal movie. It happened in frame 632. You can see two supernovas. They happen in that frame. That's when it started, when the explosion was about to start. They both happen exactly on that same frame, okay? And they keep growing from there on. But we have two observers, one very close to the two events and the other one farther away. Okay, and so what happens in the next frame of the film? Well, we got to look at this frame by frame, okay? So here we have the first frame, right? And nothing happened. And here in the second frame, we have the supernova happening, but neither of the two observers has seen any of these two events happen, okay? But the two events happen in a given frame of the universal movie, because every atom in the universe is at a given location with respect to all others. There's distance between any two atoms. There's only one frame in the universal movie. There are not 2 frames or 10 frames. There's no movie. Father Universe does not recognize a movie or motion or time, right? So these two events, this thing that's about to happen, this explosion, happened just by sheer coincidence in the same frame of the movie. Let's not talk about time or motion. Let's say it's in the same frame of the universal movie, and you can see the two observers are in different reference frames, right? In different locations. Okay, so what happens next? Well, the light from the event starts exploding, right? And it's probably going to arrive at the first observer far faster than it arrives at the second observer, okay? Because the second observer is simply too far away from the event, okay? So what happens next? Well, in the next frame, you can see what's happening. The light now reaches one of the events of, we'll call it supernova number 1, the one on the top, reaches the first observer, okay? But as you can see, the light from the second supernova, right, we'll call it the second one, the one on the bottom, is a little farther away, so it hasn't reached his eyes yet. Only the first one has. And neither of those two events has reached the second observer, okay, because he's just too far away from the two events. Okay, so what happens next? Well, now we have frame number 5 here, 635. The observer, first observer, he sees now for the first time the event of the second supernova. He's already seen the first one. And the second observer, he hasn't seen either one of them. He's still waiting for the light to come to him from either event. And we'll put this final frame here, okay? We'll call it frame 636, I think it is, yeah. And now for the first time, observer number 2 sees the event from the first, sees the light from the first event, but he doesn't see the light from the second event yet. Okay, so you can see the progression. The issue is that this event happened in frame number 2. Let me put this up here. Happened in frame number 2, 632, and you can see the sequence here of when they all see, in what frames they see the events happen. So this is the way it really occurs, and what we're saying is that 2 supernovas occurred exactly in the same frame. They can only occur in the same frame in this example. And the light reaching each observer and what they measure and how fast they're moving and all this stuff has no bearing on the simultaneity, which is a single frame of the universal movie. That's what simultaneity is in science, not in the religion of special relativity. So again, we have to put it in the right context. What is versus what people measure. What people measure is irrelevant in science. We don't care about measurement. We care about what is reality. And these people are out of touch with reality because they come up with all this nonsense based on their measurements. They say, well, I measure this. And the other guy said, well, I measure that. And so those two measurements don't coincide. And so they reach different conclusions. And they had to create the equations to justify each one of the opinions of when the event happened. So they concluded, instead of saying that the two relativists are irrational, they said, no, the event did not happen at the same time. For me, it happened this time, the other one happened that time. It's like you go to a jury, a trial, and the guy is both guilty and innocent. The defendant, he's both guilty and innocent. For one juror, or half of the jurors, he's guilty. For the other half, he's innocent. Okay, so should we flip a coin? Well, instead of giving him 10 years, we'll give him 5-year sentence because it's half the jury. Okay, so that's the way it works in special relativity. They all vote and they say, well, we'll use the equations to justify that we're all right. He's right and so am I. It's all relative, right? Okay, so how does all this affect mass? Well, we have massive problems in special relativity with what? With definitions. There are no definitions in mathematical physics, so you can't arrive at any conclusion. You cannot understand what these people are trying to translate, okay, from their math to the ordinary language. And, there's a problem there because people want to know in regular language what happened. And these people are translating their mathematical concepts and trying to do the physical interpretations with their mathematical concepts. So they bring in words such as field and energy and mass and time. And the other person says, well, I didn't understand squat. Yeah, he didn't understand squat because the presenter, the mathematician, he didn't understand squat. Okay, he says, well, I understand it in the world of math, but I cannot translate that into the language of ordinary speech. Of course not, because the language of mathematics, right, which has nothing to do with physics, right, mathematical physics, that's a contradiction in terms, right, an oxymoron, right, mathematics is, a descriptive, a quantitative language, if we can call it a language. Some guy was telling me that's not even a language because a language has to express itself, it has to be able to give you about causation and explanations and theories. And he's right to that in that sense. All languages, I don't care if it's Chinese or Greek, can express thoughts and explain things. Math cannot explain. Math is a language that has no power. In fact, it's impossible for it to explain anything. It can only describe. And these people are trying to explain how the universe works because they do give you a physical interpretation and explanation known as a theory, right? They call it a theory even though it's not a theory. There are no theories in mathematical physics that are rational. Why? Because they're trying to do the theory, the explanation, the physical interpretation with mathematical concepts. They're moving concepts around. They're saying, oh, the mass moved this and the field vibrated and the wave came down to us oscillating up and down. That's the problem. The problem is that the language is, it's not even a language, but assuming it's a language, a descriptive language. That's all it is. It cannot explain. So why do the mathematicians who call themselves physicists cross the line into physics and try to give you an explanation, a physical interpretation of how the universe works? Why are they looking for a theory of everything, meaning how you merge or unite light with gravity? Meaning, you have to visualize something. You have to say, how is gravity like light? There has to be something that mediates both. And for that mediator, it has to be a physical entity. And they're not thinking in those terms. They're looking for an equation. And so we have a problem because these people are the wrong people to be doing physics. Okay. But everybody thinks they're intelligent. And they're not very intelligent because they've come up with all this poppycock with dark matter, dark energy, and now they're in a hole because they cannot explain anything. They say they use dark matter as a spirit that they introduce into their physical interpretation. They have these invisible spirits like dark energy, dark matter, black hole, wormhole, etc. Right? They even have virtual particles. They come in from the void. These are all spirits. It's the religious people of the old who have become now the mathematicians, and they think they're scientists because they're explaining all this stuff with these inexistent, invisible, dark, black, spirits. We can't see them, we can't touch them, but they're there, right? They tell the astronomer, go look for it. Go look for a black hole. What is it? It's a zero-dimensional nothing. Okay, I'll look for it. See if it shows up on my telescope, okay? Okay, so what was the problem? The problem is definitions. It starts with the problem with definition. They never had a definition for the word mass, just like they never had one for time. And here we have a difference between good old Newt, right, and good old Einie. You can see that these two guys had a different notion. In fact, it's Einie who created a different notion of mass. He had to, in order to get his special relativity so-called theory, through, which was a mathematical description anyways, okay, because the theory part is totally irrational, has no place in science. And so this comes from the Wikipedia. It says, the notion of mass as a property of an object from Newtonian mechanics does not bear a precise relationship to the concept in relativity. No, it's not even precise. It's not even comparable. They're talking about two different things. Newton was talking about quantity of matter. Quantity of matter is something you count. Okay? What was Einstein talking about? He was talking about weight, and weight we measure. And actually, it's not actually weight, as we'll find out in a minute, but that was the closest thing you can come up with if you're talking about what Einstein was referring to when he was talking about mass, relativistic mass, all this stuff. He was talking about weight, but a different form of weight, and I'll get to that in a second. So the Wikipedia continues, says relativistic mass is not referenced in nuclear and particle physics, right? Because they can't. And they only show it in popularizations. Yeah, because they can only talk about nonsense. And so they say, we'll feed this to the public, popularizations. And that's what the public reads anyways. They don't read the so-called scientific literature, the mathematical literature. They don't read that. So you have to kind of translate it in the way you want it for them. And you can always have the excuse that, we cannot put our equations exactly in ordinary speech. We cannot translate that exactly because Father Universe speaks a different language and he doesn't have to conform to our way of thinking. And that's philosophy anyways. And they go on through all these excuses, right? Okay, so what's different between Newton and Einie there, right? Einstein, right? This is from Newton's book, Principia, right? Mathematica. The quantity of matter is the measure of the same, arising from its density and bulk conjunctly. In other words, Newton defined, in his mind at least, he defined mass as the quantity of matter. And we can all more or less understand what he's saying. We don't have a unit for the mass. We don't have a unit of mass. We could count units and say, it's 10 units of mass. In other words, 10 x's, whatever x is, right? And so, but he had this notion that, mass is just a quantity of matter. And he said, is this quantity that I mean here, hereafter, everywhere under the name of body or mass? Okay, so that was his definition of mass, the quantity of matter, essentially. Weight, what was weight in his mind? He says the quantity or amount of matter being moved. Now he's talking about the motion, okay? And so, he was referring to the fact that, an object falls to earth, right? Like a stone or whatever to the center of the earth. And he says that motion, that's what he was calling weight, meaning gravitational acceleration. So he had this notion. This is the one he put forth. Einstein had to change that. And not only Einstein, Poincaré, Lorentz, all these people had the same notion. They had to change all that because they couldn't make sense of Newton's straightforward language. And the main reason is quantity of matter, right? Like a ball, quantity of balls. You have 10 balls, that whole thing is called one body, and we call that a quantity of matter. We can all understand that. But mathematicians, they don't work with objects. They don't work with objects at all, and that's where they failed. All they do is they work with numbers. And so they had to start talking about the motion, the inertia, the energy. They started introducing all these weird, undefined concepts, which they later on gave to the public. And then the public today talks about energy and force and field and time as if it were, common language. And nobody understands what they're saying. Nobody ever, pinpointed what they're saying. And so Einstein had to change this: mass, a measure of a body's inertia. Now, Einstein understood inertia. He did talk about inertia also. In fact, he defined it in his, right before the scholium, in his first definitions, where he talks about mass, right? So he already had a notion of inertia. But that's what Einstein emphasized: the body's resistance to any attempts to change its velocity. Okay, now that has a double meaning. This is what we're going to look at here when we talk about mass. It has a double meaning. There's two meanings to this, okay? The first one is gravity. We all understand that. Body falls to earth, right? And we call that gravity. But is that mass? No, we call that weight, because we're saying it's the acceleration that the earth, for some reason, magical reason, it's apparently pulling, right? Some believe it's pushing, but it's pulling on the object, or the object is falling towards the earth, right? So there's an acceleration, 9.8 meters per second square. That's the, 9.8 meters for every, per second for every second that goes by. So it's going faster and faster and faster, okay? But that's weight, okay? So Einstein's referring to weight. But where's the catch? Well, what if you're going sideways? Now you're not falling towards the earth. Now you're falling towards the side. And that's not gravity, is it? So, well, we'll get there. Give me a second here, okay? We'll clarify that. Okay, but that's what I'm referring to here, okay? Anyways, here we have from the Wikipedia. It says, the word mass has two meanings. As always, everything in mathematical physics, mathemagics, as we call it, has many meanings, especially to confuse not only the mathematicians, but anybody who listens to them. Okay? Says has two meanings in special relativity. Invariant mass, also called rest mass, right? And is an invariant quality, meaning it doesn't change, right? Which is the same for all observers in all reference frames. What are they talking about? They're talking about if the thing doesn't move in your local frame of reference in front of you, right? You're not traveling, even if you're traveling 1,000,000 miles per second, it doesn't matter. You have this object in front of you, this rock, right? It's standing still. It's not moving with respect to anything around you. That's the rest mass. What are they talking about? Quantity of matter. That's what they're talking about. They're saying this is how many atoms, assuming if we could take the hydrogen atom, for example, and use it as a unit of mass, we would say, okay, this rock has a gazillion hydrogen atoms. That's the mass of the object. Instead, what we do, we take the rock, we put it on a scale, and we weigh it, and we say, oh, it's so many kilograms. So they weigh it, they measure quantity of matter. And that's wrong. Quantity of matter means you count. You count every unit, whatever the unit is. You designate a unit, say so many units. That's mass. But see, they couldn't do that because they can't count every atom in a rock or in anything for that matter. And so what they say is, oh, what we do is we measure. We measure, we put it on a scale, and we tell you how much it weighs. And that's the quantity of matter in terms of weight. So while the relativistic mass is dependent on the velocity of the observer. So they're saying that, if you've got an observer moving with respect to you, you're in your reference frame, in your frame of the universal movie, you could say. You're in your frame, right? In your frame of reference. You're standing still, what is called proper mass, right? And you hold the rock in your hand. The guy that's moving, he measures the weight of the rock at a different value than you do. because they're looking at the speed of light, how it intervenes in there. See, those speed of light is in the equation for mass contraction, mass increase, right? So this is important to notice. But again, quantity of matter is counting all the marbles. Weighing is, putting them on a scale and giving you a value such as a kilogram or a pound or whatever. Okay, so we have to understand the difference between counting and measuring first, and second, between quantity of matter and what Einstein referred to as relativistic mass. Okay, so here we have a situation, okay, so that you can more or less visualize what I'm talking about here, okay? We have an elephant, two elephants, in fact. We have Dumbstein, Dumbostein, and Frankenstein, okay? And we have these two elephants. They're twins. They both weigh exactly the same, 5 tons each. In fact, we don't have to have two elephants. We could have a single elephant and just do the experiment with a single elephant, okay? But the one on the left is falling at a quarter of the speed of light. The other one falls at 0.95% of the speed of light, okay? So Frankenstein there, he's going to fall a little faster than the guy on the left, okay? Now, the guy on the left is falling slower. Why? Because he's got a sun. He's falling towards the sun. He's falling towards the star, center of the star, which is a small star. And the other guy is falling to a big star, okay? And so we put a scale on, somewhere on the surface of these two stars, right? Yeah, Frankenstein is going to fall faster. Okay, that's what's happening here. And so the question is, has the mass of the elephants changed? And the answer is no. For every frame of the film that you can have a look at the elephants, they always weigh 5 tons. And here, let me show that to you. Okay. Here we have in every frame, I hope you can see that, every frame of the film, the elephants have 5 tons. And the one on the right is falling at a faster rate simply because he's falling to a bigger star, but has his weight change, has his mass change. Well, the mass has not changed. The weight has changed because as he's falling, he weighs more at different locations than the guy on the left. Okay, the guy on the left is falling at a slower speed, slower acceleration. So at any frame of that film from 632 onwards, right, the guy on the right is going to weigh more, but the mass of the two elephants is always the same. Okay, so we can't say that Einstein is correct when he says that, the change in velocity and something that changes the velocity. Well, here we have, a star that's changing the velocity of these two objects, the elephants, right? And their mass doesn't change. So, what was Einstein talking about? And again, what he's talking about is the fact that there's 3 kinds of masses invented by the mathematicians, beginning with Newton. And here it is. This is the first one. Newton has this quantity of matter. That's where he started, right? And then he's got this downwards mass, right? And he calls that gravitational acceleration or weight, okay? And you can see the equation, if we turn it around, his gravitational equation, the mass of the object is going to be equal to everything that's on the right. Force, distance squared over gravitational constant G, mass of the Earth, right? Now, of course, if you change the mass of the Earth for mass of the Moon, which is 1/6 of the mass of the Earth, well, that mass of the observer is going to be less, okay? So you can see that the mass changes, right, if we have a different object attracting it downwards, right, we'll call downwards towards the center of an object, right, like to the center of the Earth or to the center of the Moon. But Einstein developed a different notion, and he's talking about inertia, not really downwards. It's like he included all of them, the downwards as well, where he fails. But he had this one sideways, which is not really gravity. It's like you moving sideways. And the problem with that is he's talking about the velocity of light. He's introducing the velocity of light in that picture. And you can't do that here on Earth. To be able to do what he's trying to do, you got to do it out there in space, because you're going to talk about the velocity of light sideways from the observer's point of view. But what are you staring at? You're staring at gravity, because the object is falling towards the sun or a star, like we just showed, the elephant falling, right? And he, from a point of view of gravity, he's falling straight downwards towards the center of that object. Okay? So the fact that the observer is seeing the whole image sideways, Einstein got confused and he thought that, that's not gravity. Or he can talk about the inertia or the acceleration or the change in velocity, but he's talking about gravity because the object can only fall in outer space towards another celestial object, such as the Earth, the Moon, or the Sun, or any star for that matter. And so this is the issue. The issue is there is really no three notions. But if you take the second notion there, the weight, and you take the third one there, the relativistic sideways, both of them are gravity. Both of them are gravity. So there's only two notions. One is weight, and the other one's mass. And mass has nothing to do with inertia, and has nothing to do with motion. Mass is simply counting atoms, the number of atoms. In fact, here we have a very trustable source, reliable source, and that's the American Museum of Natural History. So they tell you what the difference between mass and weight is so that nobody has any doubt. It says mass and weight may seem like the same thing, but in fact these two measurements are very different. Mass is the total amount of matter. Newton, sounds familiar there? Or stuff in an object. Weight is the force of gravity on an object, on that same object. Okay? Mass always stays the same. Yeah, tell that to Heine. But weight can change depending on how much gravity is acting upon an object. Okay? So, we have all these contradictions because all these people talk about mass and weight and they say, they teach you in high school or even in college, they say, look, mass is not weight, weight is not mass. Okay? That's first of all a lie because we have no way of distinguishing between the two. And both of them are measured, which is a problem. Like if you take the grand kilo, which used to be the standard kept in France, right, of the kilogram, was there since at least the 19th century. They had this block of iron, and they said, this is the grand kilo. This is the kilo for the whole world. This is the standard to which you have to measure your standard, okay, if you want to have 1 kilo. Okay, fine, no problem. If you take that grand kilo, right, here on Earth, and you take it to the moon, what weighs 1/6 as much? Okay, so it's 1 kilo divided by 6, about 15, whatever. Okay, so what's the issue? The issue is that has the mass changed? Has the number of atoms changed? And the answer is no, obviously not. It's the same kilo standard here, the same kilo standard on the moon. They just weigh differently. And that's what, they teach you. They say, well, that's why mass is not equal to weight. But it turns out that, the mass has also changed because the way we determine mass is by weighing. We measure it. We don't count atoms. See, if they counted atoms when they left the Earth, they said, well, this grand kilo has exactly 1 trillion atoms, right? Assuming, right? And we take it to the moon, we still have 1 trillion atoms, so the mass has not changed. But that's not how they do it. They measure mass. And they said, measure 1 kilo here, and it measures different over there. So the mass has changed. And it has changed just like weight has changed. The weight here was such 1 kilogram, and over there it's 1/6 of a kilogram. So mass is equal to weight unless the mathematicians can find a way to measure, to count atoms for mass. For weight, we have no problem. We measure it. No big deal. But for mass, you gotta count atoms. And they don't count. They measure. And that's where the problem is. So that's why they have never defined mass or weight in a rational manner, and they cannot use them consistently. That's the whole problem. So yeah, if you were able to define mass scientifically, then special relativity would go down the drain. Especially in the case of mass, you say, well, it's the quantity of matter. Special relativity can't live with that because what they're trying to tell you is that this thing increased in mass. That traveled close to the speed of light. And you're saying, well, what happened? Did it acquire more atoms? Did more atoms get created from in the interstices between two atoms, what happened there? How did it increase its mass? And the answer is, well, it presses down harder on the scale. That's called weight. Sorry. Whether you do it sideways or downwards, it's called weight. In other words, gravitational acceleration. So that's the problem. That's where the whole thing is. But then, if they would have stopped there, but they had to go further because, again, they couldn't live with the speed of light. They had to exceed the speed of light, the mathematicians. So they began to find ways, mathematical ways, to circumvent the speed of light. And, of course, they always succeed, and all their papers get published. In other words, they get peer-reviewed and published. You don't publish a rational one, because if you put a rational one and you go against special relativity, it doesn't get published. The peer reviewers reject it. But if you go in there and you say, look, mathematically, I can show you, then we'll accept that paper. And they publish those papers, and they don't allow anyone to criticize those papers because, if you criticize them on the basis of rationality, they don't like that. They say that's philosophy and that they don't understand the explanation either, and that Father Universe doesn't have to conform to our way of thinking and all this other nonsense. They just want equations. And that's a problem, because this is not an issue of equations. It's a question of what is and what happened actually, really, right? That's what it's all about. And so they created this thing called negative mass that we talked a little bit about the other day, and they used all these little things with which they circumvent the speed of light. And they said, hey, we can go faster through a wormhole, or we have the tachyon that comes in from the future so fast, that it comes from the future. And we have the warp drive, we reduce up front, raise in the back, and you go faster than light. They have all these mechanisms, right? And that's what, and you might say, well, this is all speculative. No, it ain't. Okay? It ain't speculative. Believe me. If it's published every day, right? You see countless papers on all this stuff. It's no longer, for them, it's real. For you, it might be speculative. For them, it's real because they work on it. You're paying for these people to develop equations for this garbage. So don't tell me it's not real. It's real. It's hurting your pocket, but you just don't know about it, okay? And here's one fellow that proves my point, okay? His name is Jeff Landis, and he worked at NASA for several years. He was trying to develop a way of traveling faster than the speed of light, because he needed that in order to reach Andromeda. Proxima Centauri, the nearest star, right? And so he was developing an equation or equations or technology in order to get us to the nearest star. And he was there for several years, I don't know how many, and eventually NASA cut off his funds, I guess promoted him. It's called career redirectioning. You know what I mean? Yeah, they promoted him. They canceled his program because it was wasting money. He couldn't come up with a solution. And so he went out of business at NASA, and still, even to these days, he's still trying to figure out a way of traveling faster than the speed of light. And he joined the crew of all these people who try to go past the speed of light. And here's this fellow, and he'll tell you a little bit about negative mass, because that's what's required to travel faster than light. You need to have negative mass. And you say, well, that's speculative, Bill. No, it ain't. And listen to this guy so that you understand that it's not speculative, okay? You're the one who's in the wrong here. Here it goes. Okay, this is what he says. He says the following. This is good old Landis. I like the fact that he's in the Wikipedia. You can find him there. And he was at the 75th World Science Fiction Convention. Yeah, that I believe. And Landis writes, what? Hard science fiction. What is hard science fiction? A category of science fiction characterized by concern for scientific accuracy and logic. Oh, yeah. And so he talks about negative mass. Okay, and so this is what he's got to say in the paper he wrote. He says, as first analyzed by Hermann Bondi in 1957, matter with negative mass is consistent with the structure of Einstein's general theory of relativity. I thought it wasn't, because Einstein was opposed to it, but he says it's consistent with it, okay? Although initially the concept was considered just a theoretical curiosity, right? I didn't even think that it would qualify for that. It would not qualify under science or even worthy of study at all. But he says negative mass or exotic matter is now incorporated into the body of mainstream physics in a number of forms. Okay, so is it speculative? Think again. Negative mass has a number of rather non-intuitive properties, which results in possible applications for what? Propulsion requiring little or possibly no expenditure of fuel. So they're not going to do it with physical things like, booster rockets and anything like that. No, they're going to do it with negative mass. They're going to do a mathematical calculation and show you how something with negative mass can travel faster than light. Yeah, no kidding, because it's an equation, and they just put a negative sign. That's what they do. So it says negative mass, or more strictly, violation of zero energy condition, In other words, can you have zero energy or negative energy? Well, that's more or less what negative mass is, negative energy, is also a requirement for any proposed faster than light travel. Okay, keep that in mind. Faster than light travel demands negative mass. Okay, and that's what these people are writing, and this is what you're paying for them to do research on. Okay? This paper presents the basics theory of negative mass, the ways by which it can manifest in contemporary physical theory, and the counterintuitive properties that result, including possible uses for interstellar propulsion. That's what they're interested in. They want to see how you can get the nearest star by traveling faster than the speed of light, because you cannot do it traveling at less than the speed of light. For that, you need negative mass. Negative mass has moved from the theoretical curiosity to a concept fundamental to the contemporary understanding of physics. Okay? And I have to give you the second part of that because it's just priceless. Okay, here it is. 1957, Hermann Bondi pointed out that matter of negative mass is not inconsistent with the structure of Einstein's general relativity. Such negative mass matter would have odd properties. No kidding. Contemporary theoretical physics incorporates forms of negative energy. Okay, meaning negative mass. Physicists use the phrase mass, and here it is, to mean several different things. Yeah, no kidding. They have all these different notions of mass, trusting in general for the right meaning to be clear in the context. In other words, they don't define mass for you. They say, look, you'll figure it out by the context, what we're talking about. That's a good way of selling a used car, right? Negative mass reacts oppositely to all forces. Oh, force and acceleration are opposite, okay? Thus, when you push on negative mass, it moves towards you. Okay, we had that the other day where I throw the ball and the object you hit comes towards you. Well, this is what they're talking about. They're saying that you throw negative mass at something, or you throw a ball at something, and because it's made out of negative mass, instead of pushing you away, it gets closer to you. When you pull on negative mass, it moves away from you. The force of talk about your rationality, right? This is surrealistic now. The force of gravity on a negative is opposite in a gravitational field. So when M is negative, gravity pushes instead of pulls. Okay, how do you like all that? And this is a professional guy, right, who is publishing papers, right? And peer reviewers are proving all this stuff with your money, of course, right? But the inertial mass is also negative. So negative mass still falls down in a gravitational field and moves towards the positive mass. Hence, Einstein's equivalence principle still holds. That's important. If it holds, then we haven't violated Einstein's equivalence principle, right? All matter moves the same way in a gravitational field, regardless of mass, including negative matter. Sounds like science, sounds like physics, rational physics. It's for you to decide whether this has anything to do with rationality anymore, whether this is science, whether this is physics. What is this? This is absolute garbage. That's what it's called. Poppycock. How it got into the so-called scientific literature, or should we be suspecting whether it's scientific anymore? How did it get there? How did peer reviewers approve this garbage, negative mass and negative time? And warp time and traveling to the past and to the future. What is all this nonsense? If this hasn't shocked you, like Neil Bohr said, then you haven't understood it. Okay, so again, let's put it up there. Yeah, these guys are developing equations with your money, by the way, for all this garbage, including wormholes, virtual particles, black holes, dark matter, dark energy, whatever nonsense is out there. That's what they're all studying. This whole body of mathematicians is studying all this nonsense that doesn't exist, that's nowhere. They just keep giving you equations, and they can't make any sense of it, so they're kind of like at a crisis because, they cannot explain anymore. Even using, they cannot come up with new ideas. They run out of ideas within this framework. And so you're paying now for them to develop, for leprechauns and unicorns. That's where they're at now. They're playing with spirits, just like the people of old, the religions of old. And so I have a definition for what special relativity is. Specifically, special relativity, not to mention general relativity, string theory, and quantum mechanics, but specifically for special relativity. And here it is. Here's the definition for it. And I think you'll agree with me that this definition says it all. Says exactly what special relativity is. Okay, psychosis is a condition of the mind that results in difficulties determining what is real and what is not real. Okay, I think it passes that test, right? Symptoms may include delusions and hallucinations. Yep, sounds about right? Passes number 2, right? Additional symptoms are disorganized thinking and incoherent speech and behavior that is inappropriate for a given situation. Absolutely. Pass all 3 of them. And dopamine is believed to play an important role. Yeah, I think dopamine is what's happening to all these people at the university level. There's a lot of dopamine going out there. And that's why they come up talking about all this nonsense. And instead of challenging their professors, they all bow down, partly because they need careers, futures. And they say, well, I want to get a job at NASA. If I say that relativity is wrong or quantum is wrong, irrational, I'm not going to get published. I'm not going to get a job. So I'm going to play ball. And that's what everybody's saying out there. And so they all fall into the congregation and they start praying, and they believe what the priest tells them. So we're back to the dark ages as far as so-called science is concerned, physics. We'll see you next week.